everybody, and welcome to another Houdini tutorial. My name is Kate, and today we're going to be doing something a little bit different. This is the first episode in a series of episodes entitled Creating Concealed Entities of the Universe. So basically, in the series, we are going to break down a lot of quantum physics and other physical simulations and how we can replicate them in Houdini or mimic them. So this one today is a little bit lighter. It is going to be physics-based, but it's mostly going to be focusing on how we can mimic things. And the next tutorial is going to be something a little bit harder, with a little bit more theory wrapped into it. But I thought this was a good starting point for most people. So let's get started. The first thing we're going to build today is something called the cosmic web. And the cosmic web looks something like this. And you can see these are all kind of infrared, the simulations, and they are webs of almost like a fractal X-esque pattern filling up these boxes. So we're going to be building this, and we're going to be showing how to build something a little bit similar to this, as well as these purple-esque simulations. So let's get started into what this actually is. So the cosmic web is primarily composed of dark matter. The web was formed out of fluctuating energy levels from the Big Bang, and this is when space was literally boiling, so atoms, protons, electrons, all your other particles are in the midst of being formed. So nothing knows what exactly it is yet or where it belongs, and this created discrepancies in the density of the universe. So there are two factors in the universe, and those are dark energy and dark matter. Dark energy expands the universe, and dark matter, you can think of it kind of like the super glue holding everything together. So all matter attracts other bits of matter, regardless if it's dark matter or regular matter. And this is important when it comes to the cosmic web because it can explain how dark matter is clumped together and how it interacts with regular matter. Gravity is the only force that affects dark matter that we know of. The more interesting thing about dark matter is it contains something called baryonic oscillations. Or baryon acoustic oscillations, my bad. So at the start of the universe, everything was plasma, and as it clumped together, it formed pressures waves that counteracted gravity, and these pressure waves are those oscillations. So the ripples in these oscillations, and you can think of them as like big circles, are both regular matter and dark matter. Dark matter is only affected by gravity, as we stated, and the pressure that that is released into the universe is released in a process called photon decoupling. Most dark matter in nebulas or galaxies or anything else in the universe is located at a core or other rings of visible matter. It pushes out visible matter in circle patterns, but sometimes visible matter breaks free and sinks to the core of these ripples of dark matter. And a really good example of this is this nebula, which you can see the visible rings of matter, but of course you can't see the dark matter rings, which are the little gaps in between these visible matters and also the gaps in between the star and the little nebula gases itself. You might be asking, what is visible matter? And visible matter is your protons, electrons, and everything like that. And your dark matter is your theoretical particles and your quantum particles. So this ripple effect also accounts for how galaxies are formed and how they are clumped around the universe. A fun fact about dark matter ripples, they create an average distance between galaxies, and this distance is 500 million light years. So every galaxy in the universe is actually connected throughout these similar distances. So this is the average distance between everything. Unless two galaxies are colliding, this is kind of what everything in the universe where everything in the universe should be located. Corona Borealis Great Wall is one of the longest masses of filaments and fractal patterns of ripples holding everything together. Sometimes aren't connected, or they're left alone because of the container of the universe, and sometimes they create these massive filaments, which is this Hercules Great Wall, and is really cool. There's also what NASA also has to account for are voids. So in our universe, there are more voids than there is matter at this point in time because of how fast our universe is expanding due to dark energy. So this is one of the largest voids, The Keenan-Barger and Cowie void is one of the largest voids in the universe. It contains no filaments of the cosmic web and is over 2 billion light years long. The Earth and our part of our galaxy, the Milky Way, actually exist in this void, which is kind of scary because of the lack of dark matter holding us together. So our galaxy is kind of like a loose ball of matter in the universe. This simulation, there is a simulation you can already view of the cosmic web. It is called the Millennium Simulation, and it will be the reference for the tutorial. Particularly, one of their simulations, they did a near point function, and that's the method we're going to use today to build the cosmic web and mimic it. We're going to use a lot of near point tools to generate the filaments of this web. So NASA's also tried to create physical models of the cosmic web with mold and mushroom growths as their structure resembles the web structure. So you can kind of think that we either exist in a mushroom or actually a crystal, because the crystal's inner structure also mimics mushroom growths and resembles mold structures as well. So the goal of this tutorial is that we're going to build a small scale version of the cosmic web and render it to match current NASA models. Whether or not we can do it with slime growth will be up to the tutorial, but we're going to do our best. When building this model, it's important to keep in mind that the webs do not spawn from one location, rather than clumps of matter scattered around the universe or box. And we're going to be using a box as no one really knows what the shape of the universe is. There are some good guesses, but that will also be covered in a later tutorial. Our color palette will match NASA images and infrared, blue, yellow, purple. We will also need to set up a color transfer system, as well as optimize materials, cameras, and setups. And we will render an image that will then be confused with an actual image of the cosmic web, hopefully. So we may finish by making the entire setup a little bit more procedural and controllable. So if you wanted to add your own variables to the simulation, you can. This is a good starting point if you wanted to do that. We will be aiming for a 3D model rather than a 2D still of this simulation. So we can do 2D pans of it, we can blast our camera through, all that jazz. Since it is still a mystery on most of the data of the cosmic web, use your imagination. A lot of quantum physics is a lot of educated guesses and also mathematical equations. So let's look at some more interesting things. So this is the network behind the cosmic web, their actual site that you can go to, and it's pretty cool. And they have little videos and all that jazz. And they have 3 different models, and you can rotate around them and you can peer inside, and they're all a little different, and we're going to be aiming for more of the third one over here that's got a little bit more of a filter on it. And they've also got their science papers here, and it's pretty cool. So the nearest neighbors model is what we're going to kind of work with. And you've got all these cool images. So I hope you enjoy it. And let's get started. So let's get started. The first thing we're going to do is we're going to lay down 2 different Geo Nodes, because we're going to build 2 different simulations overall. Because one, we can say it might be a little bit more aesthetically pleasing to our eyes, and then the next one is going to be more nearest point functions and all that stuff. So we'll see what we can do. So we're going to go simulation 1. Probably spelled that wrong. Hold up. We're going to do number 2. And then the only light you'll really need for this project, because we're dealing with volumes and space doesn't really have a direct light source unless we're dealing with stars, will be an environment light. So we'll drag that down into the scene and we'll add that there. The first thing we're going to deal with is our materials, as these will probably be very important later on. Alright, so I've set up a bunch of materials and we'll get right back to them in a second, but I wanted to set up some other render nodes that we will need in our simulation, just so we can assign our materials now instead of getting confused with them later. Sorry I had to skip ahead here, but in this case the only way that this is going to make sense is if I organize my materials first. So we'll come back to this in a second. So now that we have our two simulations, I'm just going to pair them over here and I'm going to group them together. I'm going to drop down a few different render nodes and I'll label them and I'll get back to you in a second. So alright, sorry about that, but I created a bunch of render nodes based on what our outputs are going to be, and this is going to be the outputs for version 1 and the outputs for version 2. For version 2, we have a render web, so in close-up infrared functions. For the stars, we also have a render node and we have a render box. And what this render box is going to be are going to be our bounding box, as we've seen in these like little NASA simulations right here. So you can see the bounding box going around the entire simulation. Over here, we also have a bounding box, some backgrounds, kind of nodes for the web. So we have some extra background noise and blueness. For these two, we have some close-up glows, so we can create some nice little infrared, yellow glowing pulsing stuff. And then finally, we have some render stars and the glow around our stars as well. So that's pretty much the setup for the render nodes and what you need to label them as. All I've placed inside right now is a object merge, and we'll get to that later of what we're going to hook them up to. I've also added a transform into this object so everything aligns properly, or it should. We'll see if any problems occur. So going back to our materials, we can see that if we go to our render web, I have a material labeled billowy smoke secondary. So if we jump to that, we can go over here and we have a smoke intensity of 1, a little purpley color. Smoke density hasn't changed. The temperature field has been set to these settings. So those haven't changed as well. They've just gone from white to white. For the close-up infrared and these corresponding other nodes, they're all sharing the same shader. If you jump to it, it is down here. And we'll jump out. I've remapped the temperature, so I've given an emission color of 7, and I've given it these values for the glow. And I've changed the map to temperature density color to white. Smoke color is purple, smoke intensity is 1, density has not. If we go to our render stars secondary, I've created another shader, billowy smoke secondary stars, and we'll jump to that as well. This one is a temperature of an emission of 34. The matched temperature to density is changed to these color values, so if we look at that, and we look at that, that's what they look like. Smoke color is yellow, smoke intensity is a 4, and the density has been cranked up to a 2. So if you scroll down here to a render box, both this render box and this bounding box share the same shader, so they are not different. And if we jump to that, all it is a principal shader box with a base color that is pure white, roughness cranked all the way down to 0.039, and the metallic and reflectivity are turned down to a 0. So up here at our render web, I've created another shader for this. Jumping down to it, we have a density output of 1.82. Smoke color is a white blue color. Smoke intensity is a 1. Temperature hasn't changed other than this white. Going down to our render web backgrounds, we can jump down to this, and we can see that the smoke density is a 10. Going upwards, it's pure white. Smoke intensity is normal, and the temperature is this. Render close-up glow. Sorry, my bad. You'll find that all of these 3 nodes share the same shader. And you know, just for reference sake, I will color coordinate the ones that share the same shader so you guys are aware and don't forget that they do share the same shader. So this and this one go together. And there you go. So if we jump over the shader for the render close-up glow, we can see that the map temperature to density color is a little bit different. So if we skim through them, here are your values. Then we scroll upwards, everything's the same, and the density multiplier has been cranked down to 0. The render background web, I've created an additional background shader, which again is a billowy smoke. This is the smoke density and the multiplier, and the temperature is normal, and that's pretty much it. And jumping over to our stars, we have a glow shader. If we go over here, we've got a lovely blue color, glow ramp rate is turned all the way up, enable emission, and emission is a 9. And if we render the star glow, that has its own shader as well. So we have a billowy star glow. Smoke density is a 3.78. Shadow density multiplier is a 0.074. And the temperature is the same. And that's pretty much it for the materials. Alright, so let's get started on the simulation. So let's dive into our little node here. So simulation 1 and get started. Let's go look at some reference first. Alright, so looking at some, let's take a look at this one. I kind of like this one here. So let's kind of go for this kind of generic blob rectangle shape with these kind of spider-like filaments. So let's get started. So I'm going to start with a box. And the reason I'm just starting with a box is we don't really know what our universe is shaped like, as I've stated before. So I think a box would work perfectly, as we have some simulations, like these blue ones, where they're contained in this box-like thing. And we can easily generate a bounding box from our source points and geometry and whatnot. So I think this is a good starting point. Alright, we're back. So as you can see, I've laid down a few nodes as our starting geometry. Sorry for flying ahead, but I will be walking through just chunks of the simulation so we can set it up and proceduralize it better. So these are the starting nodes, and before I jump through them to all the changes, I'm just going to put down a little box here so we can say that this is our starting geo. And then I'm just going to leave a little note here on this side so we know where to start everything. And we can come back to it. Awesome. So as you can see, I have a box and I've scaled it up by 10 by 5 by 5 and it's created this rectangular shape. And I've also added axes divisions of 6, 6, 6. One thing we can do right now is that I think we want all the values in the y-axis of our box to remain the same as the values in the z column. So I'm just going to go copy parameter, paste relative references, and the same for the axis division. I'm going to copy the parameter, paste relative references, and then that should work from now on. And I'm going to go with this as well. I'm going to go paste relative references, but then I'm also going to go plus 5. So everything should be the same. Maybe. Go plus 4 then. That works. I've gone out and I've smoothed these down, and I've added the strength up to 50. This is really customizable. You can decide how, smooth you want this box to be, but in this case 50 works just fine. Alright, so going down to our mountain, I've added the height to a 4.23, so it's giving that more jaggedy shape. I haven't really changed anything else. I've divided it a little bit, so you're going to see in a second what it's going to do. It's going to add more edges onto our geometry. You can see it's very fine, and this is where your geometry kind of gets heavy, so just be aware of that. And then I remeshed it. And this is going to take a little while, so don't be afraid if Houdini kind of pauses for a couple seconds. Remeshes are always kind of weird. And then we have this kind of very fine geo. And before anything else happens, and before we go on to the next node, I'm going to save. This little node, this tetrahedralized node, is great. It's fantastic, but sometimes it gets a little bit heavy. So by clicking it, you're going to see right away that it's a bit slow. And alright, we have that. And basically what this has done is if we look at our remesh, we should see that it's got these little kind of hexagonal shaped polygons. So if we go up to a remesh, you might see this look a little bit differently. Or in this case, it doesn't look any different. This is really optional. This is just in case you wanted to turn off your remesh and do something different. I'll show you what it looks like right now without the remesh. This is kind of what it looks like. So you can see that it's not very clean. And in this case, I think I'm going to turn off the tetrahedralize and just put down the remesh. And then I'm going to fast forward a little bit and I'm going to cache this out. Because always with your geometry that you're starting off with, I always think it's a good idea to cache it out, just in case anything bad happens. Awesome! So there's our geometry. And now we can move on to the next step. The next step is going to be laying down a null. And what this null is going to do is going to help us in a little fun way, proceduralize everything and change our values over time. So a really cool thing that you can do with nulls is store values in them. But the one thing you have to keep in mind is you have to turn off forbid linking at parameters from outside of the subnet. This is going to make your life a little bit easier and allow you to link parameters from other objects. So what we're going to do, because we've already set up some relative references on this null, we're going to only copy over the size on the y-axis and the axis division in the x-axis. I'm going to create a folder in my null called Start Geometry. And then we're going to just copy and paste our values over. Copy parameter. I think one thing we have to do is go over here and just put that in there. And if we click apply, you should see right away this appear. And then if we go over to our null controller, we can see that this is over here. Kind of cool, right? Yeah, but we can also see that this is at a 4 now. Not sure why. Okay, you know what? We'll just delete the channels here. Oh, and a fun thing you can do if you screw up like I just did, you can go delete parameters and it will delete your parameters, which is fun. Not everyone knows about that. And then you just hit apply and everything should turn out fine again. So we're going to drag this over here to our size, and we're going to just rename this size box. And copy that, and copy that, and then we're good. Then we're going to go to our axis divisions, put that in there, and we can just go axis divisions box, axis divisions box, and hit apply, and they should be underneath a folder looking like this, which is good. Already I see a certain problem. If you can see, the problem is that because we copy parameters over, I'm going to delete the channels there. Channels, and just correct those. My bad, I thought in previous examples of this file that I was building up to, this worked just fine. I'm sorry it's not working now, but that's what happens. And we hit apply and accept, and these over here should still be good, and those look good. Awesome. So if you go over to smooth, I'm just going to drag this over as well, and just change this from strength to smooth box. And then we're going to go to our mountain and we're going to copy over the height of our noise. So we're just going to go how height noise and our divide, we want brick group polygon, so we're going to add that down there. We're also going to go over to our size, put that there. So we're going to go change that to size divide. And we'll save and apply. And then we go to our remesh. The only thing we really want to change over is our target size, so we'll drag that out as well. So mesh and apply and accept. And suddenly everything is in our controller, which is great. And we will have access to that later. And now I'm going to save and we're going to move on to the next part of this, which is creating some more strands and the VBDs and the arcing little pathways that we see in our pictures. Alright, so now we get to create the filaments of the cosmic web. And the cool thing about the filaments of the cosmic web is, as we previously discussed, they are based on finding the shortest pathways between different points or globs of matter in the universe. So what we want to do is we want to create a randomized system of pathways that can be formed inside this little squished up mountainy box that we've created that can mimic the filaments of the cosmic web. And now this is where you could use Vex, and I'm well aware of that, but I'm not a Vex person. So let's use a lot of different ways of trying to find this. And also one way we can get around using Vex is using the find shortest path tools in Houdini. This is one of my favorite tools, but is based around the idea that it can only work with 2 groups, and in each group the same amount of points has to be present. So let's get started on how we can use it. So with this first group, I've created a group called Start. This group is a start group of points. So if we click on it, we should see a base group of 4. And what this means is that our start group is only sampling 1 point that has a value of 4. And let me show you what I mean. So if we go to here and we go to our display, go to point size and just push that up there, should see a yellow point on here somewhere. Okay. Hold up. I'm going to visualize this better for you. So I'm going to lay down and delete just so you can see what's in our start group. So we're going to go to points, start, and delete non-selected. So what you should see in there is it's selected 1 point. And that 1 point is, I've changed it over onto that side so you can see it, but it's group 12. If we go back to the original number, it's group 4. And honestly, choose whichever value you like. It can be completely randomized. As we said, like, all matter in the universe is spread out randomly and distributed unequally, so starting points can be different. The end group is actually just a group of the remaining points. And if we go here and we add another delete for you to see what's in the group, you'll see that it's once again getting the points and it's labeled end. And what it's doing, this group, it says it's a group by range instead of a regular start group, and it has a range filter. And this value up here can be randomized to any of your particular tastes. In this particular case, I didn't want to select all the points on our geometry, but I wanted to select within a range of points on the geometry. So if we go here and we say this, there we go. delete non-selected, we can see that inside this group is a bunch of randomized points right here. If we go into find shortest paths, we can see suddenly it's created a pathways for these groups. And something that looks very familiar, almost filament-like, from a start point to an end point. However, it's not actually going into our little box here, and we can come back to that later with some different filaments and see what can happen. But yeah, for the find shortest paths, we've got from outer paths, from any start to each ends. And if you scroll through down here, you might see some different results. In this case, I've chosen this one. For path costs, nothing, nothing. So you're pretty good to go. Start points are the start group, end points are the end group. Pretty cut and paste. We fuse these points together just in case they're overlapping, and then we've smoothed them out a little bit. So you can see they went from jagged to together. If you like jagged, feel free not to use this, but it's up to you. Once again, I've added down a null, and I've put out big filaments. So these are going to be the largest filaments in the cosmic web. And just so we can know where we are, I'm going to color code this null yellow, just so we can see it. I'm going to go back to our controller, and I'm going to go to Edit Parameter Interface, lay down another folder, big filaments. Turn off this for now. Go to our start group. Our base group is 4, so I'm just going to put that base group in here. So we can randomize our base group if we feel like it. Base group points. And if you wanted to add more than one base group, you totally can. It's up to you. And that's why we're procedurally doing this. We've got end group. I'm going to actually change this from base group points to start group points. That might be a better fit. Let me go to our end group, and the cool thing about the range filter is don't grab select here and drag it over. Grab the of, otherwise it will grab the one instead of the range of values we want to select. So if we hit this, you should see that appear. So we're going to just change this to end group points. Find shortest path. We don't really need to put anything in here. We're all good to go, honestly. Fuse, we're good to go. We don't need any of that. And smooth, we're good to go. So we can apply and accept and go build the other filaments. And we'll save before anything else happens. So now if you go over here, you can see that I've set up 2 additional filaments. And you can see all of them look like this. When they're combined together, when they're merged down here. What I'm doing currently is I've decided what we're going to do is we want to build the filaments that are basically holding this, the other parts of the universe together before building inside. So this is what this is for. And once again, it's building on the fact that we can find shortest path and we can smooth it out and have our base end and end groups over here. If we go over here to our start point, you can see over here that in this little group up here, it's once again labeled start. Its base groups are 6, 2, and 8. And if we click this over here, it's selecting 3 points. So just keep in mind, any amount of numbers you add in your base group, the more points you're going to get as a starting point. Same goes for the start group over here. This has a base group of 12. It's grabbing point 12, if that makes any sense. If we go over to end over here, we can see that it's once again a group by range, and is labeled end, and the same goes for the one over here. So they both share the same value, And you can see that they are selecting within that range. All three of these share the same value, so you can hypothetically, you know, copy relative references of this one. And I'm going to copy parameter and paste in there. And we should be all good to go in that group. That makes any sense. For the start groups, we're going to proceduralize that and put that in our null. We don't really need that too much. But let's move on to the find shortest paths for these filaments. If you go over to this one, you see it's from any start to each end. And the max search radius is 100. And the same goes for this one as well. And we've got the start group and the end group. The smooth over here is a 1.4. And then the one over here is also a 1.4. So we can probably copy and paste those at a certain point. I've once again added a null. So we've got out additional filaments. And then we've got out additional filaments secondary. So let's add these into our controller. I've also added controller web at the end. I think that's better. And you will know what? Let's give it a little bit of color. I'm going to save. And then we can go like this. And under big filaments, I'm just going to put that folder underneath there. I think that this is going to be the better way to organize our folders. So I'm just going to steal this name out, additional filaments, put it in there. And I'm also going to add another folder, which is additional filaments secondary. There you go. And we're going to apply and accept. Go up here to our start group. Base group we'll put underneath additional filaments, but you can see we've got an error because each time that you open up your null, you do have to turn this off. It always defaults to that. It's a little bit annoying. So we're going to go start group. And our endpoints are good to go, so we don't need that. We can smooth these out, so we'll just put that there. And the same goes for over here. So base group. And our smooth. Right, actually let's not put that in yet. What I want to do is go back over to our other smooth, which was I believe this one. Filter quality we're not going to change, but let's just press apply and accept. And so for this one, now that we have that value there, we'll copy the parameter, put in there. Copy. And that should be the same. And now we're good to go. Awesome. On to our next step, which is to create the filaments inside our shape. So I'll be right back. I'm just going to check something.